unlocking hidden dimensions inside a single photon. The quantum light revolution. Imagine if a single particle of light could carry not just a single message, but dozens, hundreds, or even thousands of bits of information, all at the same time. Sounds like science fiction, right? Well, physicists are now doing exactly that. They've found ways to sculpt individual photons in space and time, unlocking hidden dimensions inside them, and the implications could completely transform quantum communication, sensing, and computing. For decades, photons, the fundamental particles of light, have been the backbone of quantum experiments. We've used their polarization or the direction of their oscillation to encode quantum bits or qubits for secure communication and basic quantum computing experiments. But until recently, the toolbox for manipulating photons beyond simple properties was almost empty. We could send information, but only one layer at a time. Now, a team of researchers from the University of the Witwatersrand in South Africa, in collaboration with scientists at the Universitat Autònoma de Barcelona, has fundamentally changed the game. They've shown that by carefully controlling not just the polarization, but also the spatial patterns, timing, and spectral properties of photons, we can create structured photons. These are engineered particles of light capable of existing in multiple dimensions simultaneously, essentially transforming a single photon into a tiny, high-dimensional information carrier. So, what does this actually mean? By shaping the quantum wave function of a photon across multiple degrees of freedom, scientists can design highly complex quantum states. Imagine taking a single photon and giving it a spatial pattern like a swirl, assigning it specific colors or wavelengths, and orchestrating its arrival in ultra-fast time sequences. Each of these layers becomes a separate channel for information. Professor Andrew Forbes, the lead researcher from Wits University, calls it the Quantum Light Toolkit. 20 years ago, this toolkit barely existed. Today, we have on-chip devices that can generate, manipulate, and measure these structured photons with remarkable precision. This progress is no longer just a laboratory curiosity. It's paving the way for practical quantum networks, high-resolution quantum imaging, and ultra-secure communication systems. High-dimensional encoding is one of the most exciting aspects. Traditional qubits rely on a simple binary system, 0 or 1, but these structured photons can encode many more states simultaneously. That makes them incredibly robust against interference and loss, a critical feature for building secure quantum networks and transmitting large amounts of data. In other words, one photon can carry exponentially more information than was ever possible before. The practical impact is enormous. High-dimensional structured photons could make quantum communication systems faster, more secure, and capable of transmitting far more information than current technologies. Quantum sensors could exploit the multidimensional nature of photons to measure distances, magnetic fields, or other physical quantities with unprecedented precision. Moreover, researchers are beginning to explore topological properties in these quantum states. Adding a topological layer means that even if a photon is disturbed or partially corrupted, its quantum information can survive, like encoding your message inside a knot that cannot easily be untouched. This could dramatically improve the resilience of future quantum networks, which today are extremely sensitive to environmental noise and loss. What most media is missing. While mainstream coverage often highlights flashy headlines about faster quantum computers or unhackable communication, the deeper story is subtler. The real revolution is in control over the photon itself, not just the qubits they carry. Most media fail to emphasize that this is a multidimensional engineering problem. Researchers aren't just observing quantum light, they're actively designing and sculpting it. This precision control over structured photons is what will truly enable scalable, practical quantum technologies in the coming decade. Another critical point that's often overlooked is the challenge of long-distance transmission. Structured photons, particularly those relying on spatial patterns, can struggle over conventional fiber optic networks or atmospheric channels. That doesn't mean they're impractical. It means we need to rethink the physical infrastructure for quantum networks, possibly integrating free space channels, specialized fibers, or topological protections to ensure robust communication. Future outlook. Looking ahead, the potential is staggering. Imagine global quantum internet nodes connected by photons carrying tens of bits per particle, traveling through networks designed for maximum resilience. Imagine quantum sensors detecting subtle changes in gravity, magnetic fields, or chemical composition with a sensitivity impossible for classical instruments. The field is also moving toward on-chip integration, which could shrink entire quantum photonics labs down to devices that fit on a silicon wafer. That means compact, scalable quantum technologies could move out of specialized labs and into real-world applications, ranging from secure communication for governments and banks to high-capacity data transmission and next-generation medical imaging. However, challenges remain. Increasing photon output, maintaining entanglement across multiple dimensions, and ensuring stability in realistic optical environments are active areas of research. But the momentum is undeniable. As Forbes puts it, we're at a pivotal moment. Structured quantum light is leaving the lab and approaching practical reality. Closing thought. In the end, what excites me most is the shift in perspective this represents. Instead of passively observing quantum phenomena, scientists are actively designing reality at the level of a single particle of light. It's like discovering that your flashlight doesn't just illuminate, it can carry a library of information in a single beam. And in the world of quantum technology, that's exactly the kind of leap that could redefine computing, communication, and sensing forever. We're not just learning to use photons. We're learning to write the rules of quantum light itself. And that, my friends, could change everything.